Well, we're now back with part 3 of the introduction lecture, lecture 1 of the Introduction to Radar Systems course. Now, what are these pulses we send out? 1 minute I'm telling you that we're sending out waves. The next minute I'm saying pulses. Well, what do we transmit? Do we transmit waves or pulses? In fact, we do both. What we do is we turn on the transmitter and we send out a wave which is modulated or varied by turning it on and then a little later turning it off. And this is and what you'll usually see in a visual depiction of a pulse is not the up and down of the sine wave, but just its envelope, as it's called, the pulse envelope of the electromagnetic wave. Okay? And notice this particular electromagnetic wave, the frequency is perfectly constant throughout the whole pulse. Okay. And that's what we have up here, a pulse at a single frequency. And its envelope would be up, over, and then down. And if we drew the frequency of this pulse as a function of time, it would be constant. There's one waveform that we use, and we use it to get a better accuracy out of a pulse. When we're making better range accuracy of the precise location and range of the target. And we can do that at the same time by having long pulses, which will give us lots of power. And we can do that by either changing the phase of the frequency of the pulse as the pulse is being transmitted. And this particular example, what we're doing is we're changing the frequency of the electromagnetic energy in the pulse as it's being transmitted. We're going from a lower frequency to a higher frequency. And here's a visualization of that. And that is happening linearly. The frequency increases linearly along this length of time that we're transmitting. And that's called a linearly frequency modulated waveform. We'll talk about that later and why we use it, but I want to bring in the definition now. Now, I've mentioned that in a qualitative sense earlier, and it makes perfect common sense. You send out a pulse of energy, it's going out at the speed of light, it hits a target and comes back. Well, if one target is twice as far away, it's going to take twice as long for the echo to come back. And what is exactly the algebraic relationship between the target range and when you measure that echo is coming back relative to when you transmitted the pulse? And that's what this goes over. How, in the simplest sense, how we measure range. We send out a transmitted pulse, it hits the target, the reflected pulse comes back, okay? And so the time that it takes to go out and back, the round trip time, that's the time between the transmitter turns on and when we receive it, is the round trip time. And the pulse goes out and back at the speed of light, so it's speed. And so we know that the range is the velocity times the time. But the range that the target goes out and back is twice the range to the target because it's got to go out and then back. So there's a factor of 2 here. Twice the range to the target is the speed times the round trip time, because that time is to go both ways. So the target range is the speed of light times the echo, the time from the turn off till you hear turn off the transmitter goes on and off till the echo comes back, that round trip time, divided by 2. There's a factor of 2 in there. Okay. Now I want to just reiterate this concept of gain. We went over it a little bit quickly. Here we have on the left the visualization of an antenna, a tower, and on top of it is a little transmitter with an antenna that's sending energy out isotropically in space, uniformly in space, so that the energy, a pulse wave, say, goes out like an expanding sphere. Okay? It's going in all directions equally likely. All angles are equally likely. A sphere expanding. We call that an isotropically radiating antenna. Okay? Now the antennas that we build, we want to focus the energy in one direction. And the amount of power that we're able to focus that energy, the maximum amount, is over what you would for an isotropic antenna. It's called the antenna gain. And you can see here a parabolic dish antenna. When we get in and discuss the antennas a little more, we'll go over why parabolas and all that sort of thing. But the gain, the antenna gain, is just the increase in power over an isotropic antenna. It's a definition of gain. Now I talked a little bit about propagation, and I alluded to the fact that as the radar beam goes through the atmosphere, things can happen. And I just want to mention quickly that there are 4 things, and we're going to spend a whole lecture. We're going to expand this view graph in the 3rd lecture of the course into a whole lecture. And we're going to talk about these 4 things. As the radar energy propagates from the antenna to the target and back, the atmosphere will attenuate the signal. Okay? It'll interact with it. Turns out water and oxygen in the atmosphere will attenuate it. Also, some of the energy from the beam can bounce off the Earth, come back up, and reflect up and interfere. You remember those waves, constructive and destructive interference. So that at some angles you'll have an increase in propagation, they'll constructively add, and some they'll destructively. You'll have a thing called lobing. We'll talk about that. So reflection off the Earth's surface is important. And depending upon the characteristics of the atmosphere, the radar and the ground and the edges that the wave goes around, you can have bending of the beam, and the beam can bend over at low frequencies over the horizon that your eye would just see over straight line propagation. And in addition to that, the fact that the Earth's atmosphere decreases in pressure, temperature, and the humidity, the water content. Those changes, because you all know, down at low, there's less atmosphere on Mount Everest, but that change in atmosphere, that change in what is the index of refraction, which is the ratio of the speed of light in a vacuum to the speed of light in that atmosphere, that change in the index of refraction, which is a measure of the density, causes the beam to bend. And we're going to look at that and how that happens and how it affects the radar. Okay, now we're going to have just a little bit more. I probably said 3 sentences before about the radar cross-section. I want to now spend a view graph. We're going to have a whole lecture on the radar cross-section of targets. As we mentioned when I went over very quickly in the radar equation, what we have is an incident power density of watts per meter squared, power per unit area. And that's going to hit the target. And the radar cross-section is the effective cross-sectional area of the target as seen by the radar. An effective area, well, its units you'd expect to be meters squared, length squared, an area. And that's that factor in the radar equation, which tells you to that wavelength of microwave energy, how big did the target seem. Now, when I look with my eyes at an object, I'm looking with very, very short wavelengths. and the electromagnetic cross-section I see are the optical sizes of things. You know, something that's an inch by an inch physically is an inch by an inch. But at microwave frequencies, the effective area can be sometimes bigger or smaller than the physical size of the target. Okay? We all know that people have made airplanes that are physically quite large, that appear to be an awful lot smaller than the physical size of that target. You know? And so we're going to talk a little bit about that, and generally about radar cross-section. Okay? Next, we're going to spend a lot of time talking about signal processing. One aspect of signal processing is that part called pulse compression. Another is Doppler processing. And here I said 2 sentences a couple of view graphs back. I'm going to spend a view graph. You know, we're hit sometimes with a dilemma. The accuracy with which you can measure in range, in a simple pulse, is just the pulse width. You can't tell whether if the target is a very much smaller than the pulse, you can't tell the range any better than the resolution of your instrument to measure it, the pulse width of the transmitted pulse. So if you increase the pulse length, you can get more energy on the target, but you lose in range resolution. But you want both. Is there something you can do? What you can do is you can transmit one of those linear frequency modulated waveforms. And here's a visualization of what one of those uncompressed, unprocessed pulses would look like. And then what we do is we send that through some processing. It's called a matched filter, and it's the processing that optimizes the signal-to-noise ratio. And then we get out a compressed pulse, which is very precisely where within the range corresponding to that pulse width the target actually is. So you can literally see within a pulse where it is. And this process called pulse compression is a signal processing function. Okay? And notice just up here where we have a radar antenna. Of course, we know there's a transmitter and receiver behind it, and it's transmitting out a pulse. And if the length of the pulse is 1 millisecond, that corresponds to a range of 150 kilometers. So if we wanted to transmit a pulse that long, full of that much energy to see a target far away, you haven't got very good range resolution at all. That's just a little visualization to say, hey, if we modulate, change the frequency of the pulse, and then send it through a matched filter and do the process called pulse compression, we can 1,000 to 1 we can find, depending on how we do the process, 100 to 1, 1,000 to 1, 10,000 to 1. Big numbers, we can see where within that pulse the actual target is, get our range resolution down, and at the same time have a big wide pulse with lots of energy to see the target. I'm going to spend a big chunk of one of the lectures on pulse compression and a lot on signal processing. Now this talks about the whole concept of bandwidth. Okay? Now you saw before with the linear FM waveform how the frequency went from one number to another number. It linearly changed in the course of the pulse. Okay? That frequency extent, that the frequency changed over the course of the pulse, is called, for a linear FM waveform like we show here, that's the bandwidth. Okay? And when we process it through pulse compression and convert the time to range, the width of the pulse, our resolution, is the speed of light divided by twice this bandwidth. So if we have a high bandwidth, like as is visualized here, and then we do pulse compression, when the denominator gets bigger, the answer gets smaller, so we'll have much better range resolution with wide bandwidth. Now, what else does this say? Well, it turns out bandwidth is easier to get at higher frequencies, absolute amount of bandwidth, than at smaller frequencies, because it's pretty easy to get about bandwidth of 10 or 15% of your center frequencies. So if you're at a radar that's 1 gigahertz, it's pretty easy to get a tenth of a gigahertz, or 0.15 gigahertz of bandwidth. If you're building a radar whose central frequency is 10 gigahertz at X band, you can get bandwidth of 10%, say, a gigahertz. And that is a lot better, a factor of 10 better range resolution that you'd be able to get, because you can get better bandwidth at the higher frequencies. Okay? Now, what does this mean? Why is bandwidth important? Why is that range resolution important? This could be any target. It could be an aircraft. It could be a missile. It could be just any complex target that a radar was looking at. But what I've plotted here, and I've left off the axes, and just to give you a rough qualitative idea, if I have a radar whose resolution in range is very fine, say it's of these tick marks. Let's just look at this whole length is 1, 2, 3, 4, 5, 6, almost 7 marks. And say I have my range resolution is very, very small, a small fraction, one of these tick marks. Then I'm going to see all the different scattering points on this target. I'll see, as an individual different scatterer, I'll see the tip, the edge of the tip, right here where this cone turns into another radius. I'll see these different points. I'll see where this stage of the missile is a juncture. I'll see that right here. I'll see the fins in back, and the back of it I'll see. And as I have lower and lower bandwidth, it'll just appear to be one big bump. So for understanding the characteristics of a target, no matter what that target is, higher bandwidth is very important. And with very low bandwidth, I can't tell much of anything about the target. And with high bandwidth, I can tell a lot more about it. That's why bandwidth is important. You saw this visualization before. In the red, we have the noise, and then we had a target here in the center. Okay? Now I'm going to bring in the concept of putting in a threshold. How do we tell that a target is there and it's not noise? Well, what you have to do is to set a threshold saying, if the power is greater than a certain amount when I'm listening, yeah, it's probably a target. And that's in the case where the noise background is moving up and down. I want to point out that the noise is a random variable. It means it's randomly going up and down. And there's a small probability that it can go very high. But it's most probable to do what its average is. Okay? And to just have a little bit up and down is not too probable. And not very probable that it'll go up. But sometimes the noise can go above that detection threshold, and we call that a false alarm. We thought there was a target at that location, that range, but it's really the noise fluctuated above it. Okay? And here we have a target detected, and over here in blue we have a weak target that was really there, but it was below our threshold, and we missed it. So we can have, so in fact, because targets, all targets you're going to learn don't have a steady return. Some do, but a sphere would, any orientation. But complex targets like aircraft, the target will fluctuate up and down. Or propagation could be all sorts of, or its aspect angle could be changing, and that could change the return that you get. So you've got literally the target's a random variable, and the noise is a random variable. Here we have dashed line at the root mean square, it's sort of the average noise level. You can sometimes miss a target because maybe you don't have enough power, it's very far away, or lots of different things. So you can have missed targets, and detected targets, and false alarms. And this is all, it's a probabilistic process. We're going to study that probabilistic process in one of the lectures on detection. Now, when you have a target, and it's like that one that was weak in the other one, you might want to add together the return from different pulses. And if we take pulse, here's you see the voltage of a signal that's buried in the noise. The signal-to-noise ratio is less than 1 in natural units, or less than 0 dB. If we coherently add them together, remember, keeping the target phase, then the target will move up, but since the noise is random, it won't move up as much. And what will happen is the signal-to-noise ratio will be increased by n, the number of pulses that you're coherently integrating. Okay. Now I want to go over the Doppler concept. I'm sure you've often had say a car went by. Most often, I think most of us, it's a train going by. You're at the station, and you hear the train. Its whistle blows as it comes into the station, but it doesn't stop at your station, And you hear a high-pitched tone of the whistle. And then after it goes by, and you listen, maybe you haven't noticed this, the tone is lower frequency. It goes, sort of, okay? What you're hearing when that happens is the Doppler effect. And the Doppler effect literally says that the frequency that you hear depends on the motion of the emitter of that frequency relative to you. So if I have a target moving towards me, the carrier frequency will be increased a little bit because of the Doppler effect. And it will be decreased a little bit if the target is going away from me. Okay? Now, this visualization shows you sort of how that happens. We have a wavelength here, and we're sending out a pulse of energy. Remember, the wavelength is equal to the speed of the wave divided by the frequency. And say we have a little man here, right at all the peaks. And they're moving at the speed of light, and here we have our target. And it's moving towards the man at a velocity v. Okay? Now, when the first man hits that target and comes back, he's going to head back. Okay? Now, when the second man heads back, the target is going to have moved closer than when the first man hit it. So the distance between these two guys is going to get less. They are frequent, that distance being the distance between the peaks. So the frequency is getting higher. And as we see, the other men coming, okay, so that the distance between the peaks, which was greater here, is less here. The wavelength has gotten shorter, frequency higher. And that's called the Doppler shift. This is a nice little cartoon that shows it. Okay? We're going to be able to use the Doppler shift to separate targets that we want to see that are moving from backgrounds that are moving slowly or aren't moving at all. Okay? And that's why Doppler is important. Clutter returns, which is a term used for all that stuff out there that we don't want to see that are real targets. Things like rain clouds, things like flocks of birds, things like buildings, things like the ground, that the radar's pulse illuminates and energy comes back. We're not interested in them. If we're looking for aircraft, we're going to want to reject them, and we're going to use that using the Doppler effect. Okay? Particularly if we have an airborne radar that's looking down at a target on the ground, you've got to take into account the fact that both the radar and the target are moving, and that's going to make the situation very complicated. But Doppler lets you separate things that are moving from things that aren't. That's the message I want to leave you with. And when we look at the relative power of the Doppler spectrum, the relative power versus velocity of different kinds of clutter, we see that land clutter, and this is a logarithmic scale, each one of these is a factor of 10. Land clutter is very, very high. And then sea clutter. And then rain and chaff. Chaff is aluminum dipoles that people throw out of airplanes or eject from different entities when you want to cloud up the sky with targets. And birds, discrete targets. The fact that this is broad means it's diffuse. They happen over a lot of velocities. And here we have our target. This target's up at 100 meters per second, a couple hundred miles an hour kind of thing. An aircraft in its radial velocity. You can see you ought to be able to separate them. So we're going to use that to a great degree. Here we go back to our block diagram. So we've hoped in this lecture we've gone through all these different pieces very, very, very lightly. In a sense, you've had in this first introductory lecture sort of radar an hour and a half. What the whole course is going to do is give you 8-10 times that knowledge. Okay. And now let's go over the agenda before we adjourn for this lecture. This first lecture has been an introduction. We'll move on to the radar equation. Then we'll study propagation effects, the target radar cross-section, and then we'll look over the detection of signals and noise, followed by pulse compression. I'll probably break these down into a part 1 and part 2 of the lecture. Antennas, radar backgrounds, that clutter we just talked about, and chaff, and the different ways we do signal processing, so-called moving target indicator, and pulse Doppler techniques. These are techniques of rejecting clutter and seeing targets in their presence, then tracking and parameter estimation of the targets, followed by a lecture on transmitters and receivers. Okay. And here is some different references.